At 8:13 on the morning of August 17, 2009, the floor of Russia's largest hydroelectric power station lifted off its bearings. Within 9 seconds, 75 people were dead. A steel turbine cover weighing 2,000 tons launched into the rafters. A column of pressurized water punched straight upward, flooding the powerhouse. After the water was pumped out, forensic teams found 3 massive turbine units completely destroyed. 5 more units would require partial reconstruction. Investigators began their work by examining 49 broken steel bolts recovered from the pit. They were laid out in cardboard trays under fluorescent lights, categorized for metallurgical testing. Microscopic analysis of the metal revealed a specific pattern. 41 of those critical, load-bearing bolts had been cracking for years before the disaster. The discovery of the pre-existing cracks shifted the investigation. The question was no longer about a sudden, invisible rupture, but why a machine showing every physical sign of failure was kept in operation until the bolts finally gave way. The Sayano-Shushenskaya dam sits on a remote stretch of the Yenisei River, housing 10 Francis turbines. Each unit was designed to generate 640 megawatts of power over a 30-year lifespan. In a Francis turbine, water enters through a spiral casing to spin a runner the size of a small house. This creates an immense upward force. 2,000 kilopascals of pressure constantly push that cover up. The only defense is a ring of 80 thick steel studs anchoring the cover into the concrete, holding the reservoir's weight. If these bolts foul, the top cover loses its anchor. It becomes a piston driven upward by the full weight of the river, turning the turbine hull into a column of water and steel. Forensic teams found a common failure pattern. The smooth area is a fatigue crack marked by concentric rings, each a record of 1 revolution. On 8 bolts, this fatigue zone covered over 90% of the cross-section, leaving only millimeters of intact steel. The investigation also found that at least 6 bolt holes had no nuts installed at all. There was no maintenance record explaining why they were missing or if they had ever been fitted during the previous 30 years of operation. By the morning of August 17th, the massive cover was effectively resting on its own weight, held in place by a ring of fasteners that were, in engineering terms, already broken. The event that finally pushed the bolts past their limit began with a fire at the Bratsk power station. The fire severed grid data lines and disabled the automatic systems that allowed several plants to share the load of frequency regulation. Because of the fire, Turbine 2 at Sayano-Shushenskaya became the lead regulator for the Siberian grid. At 8:12 a.m., the machine was forced to reduce output, dropping into a not-recommended zone, Power Band 2. Here, water pulses matched the machine's natural resonance. The massive load shifted onto the weakened fasteners. The first bolt snapped, and the rest followed. The resulting blowout was less of a mechanical failure and more of a hydraulic explosion, launching the turbine cover and the spinning rotor 15 meters across the powerhouse. The official report from Rostekhnadzor, the Russian safety agency, moved the focus from the metallurgy to the plant's own inspection logs. They found that the condition of Turbine 2 was well documented. While the maximum permissible vibration for the turbine was 160 micrometers, inspectors recorded a steady climb throughout 2009. By the final week, vertical displacement reached 1,500 micrometers, roughly 7 times the allowed maximum. One operator described the steel handrail of the upper gallery, 60 feet away, vibrating hard enough to be felt through his work gloves. He reported it, but the unit remained the lead regulator for the grid. The inspection regime at the plant focused primarily on walk-around checks. Because the bolts were hidden deep inside the turbine pit, there was no regulation or procedure that required workers to disassemble the unit and check them. For 10 years, the bolts cracked because nobody was looking for them. They measured what was easy and treated the absence of visible bad news as proof of safety. This left the technical reviewers to ask why nobody stopped the machine if the vibration logs were so clear. The report identified a diffusion of responsibility. The plant director could stop a unit, but reported to the grid dispatcher. The dispatcher reported to corporate. No single person had the authority to trigger a shutdown. As the vibration numbers climbed year after year, they stopped being treated as an engineering emergency and simply became a habit for the entire chain of command. Reconstruction took 5 years and cost 40 billion rubles. The new turbines are equipped with continuous accelerometers and hard safety interlocks that automatically take a unit offline if the vibration exceeds 200 micrometers for more than a few minutes. The recovered bolts were not unusually small or made of exotic alloys. They were ordinary parts used exactly as designed, but operated in a way that the original designers had explicitly warned against. Metal cracks at the speed of physics, but as the investigation concluded, the institutions around it can crack much faster when the condition of a machine stops being anyone's specific job to know.